Hello, my name is Adil and welcome to my presentation on force convection with velocity-temperature coupling using Lattice Boltzmann method. The inspiration for this work came from the work that we do at the combustion lab, where we simulate our combustor in CFD to study chemistry evolution. I also found this really cool project where they simulated convective heat transfer in porous media using Lattice Boltzmann method. The goal of the project is to simulate flow around obstacles in an inlet-outlet domain. I'm going to use a conventional D2Q9 lattice, and I'm going to use steady state. For the walls, I'm using specular reflection to enforce free slip. For obstacles, I'm using bounce back. For the inlets, I'm using the Zhu and He boundary condition to impose constant velocity. And for the outlet, I'm using the same boundary condition, just flipping the terms to calculate for F6, 3, and 7 that point into the domain. Important to note, there is a pressure drop from inlet to outlet. The way heat impacts velocity is through the Boussinesq approximation. We find the buoyancy force, and it's important to know the thermal expansion coefficient is kept constant, while the gravitational term is calculated through Rayleigh's number, which helps us keep the discretization for the lattice, because the viscosity and length, characteristic length, are dependent on the grid. I use a constant Prandtl number of 0.71, and I'm using the GUO enforcing scheme to find the force and apply it through the collision step. The way velocity impacts heat is through convection, and just using the conventional definition of the temperature distribution functions helps us capture this phenomenon. Now, if we look at the results, we see streamlines and counterplots. First, we see vortices forming behind the flat plate. We definitely see the temperature being shifted by the flow. We can see it's kind of lagging behind the obstacle. And we definitely see the buoyancy forces pushing the flow away from the flat plate because the flat plate region is hot. Now, to validate my solution, I'm using the Heat Transfer Today developed software, which is essentially an analytical solution based on the Blasio solution for a flat plate that also captures heat transfer. Specifically, I'm going to look into the temperature gradients at the surface, and here you can see I input my Reynolds number, Prandtl's number, I input the same thermal boundary conditions, and study the distribution. If we look at graphs, we indeed see that with finer grid, I am approaching the trend of the analytical solution. However, we do see some discrepancies, especially past 10 or 20% of the flat plate. Now, it's important to note that first of all, I'm simulating the whole 2D domain, including top and bottom of the flat plate. Also, my flat plate is not thin. It has a width, and the flat plate in the analytical solution is in an isolated domain where it's just the flat plate inlets and the flow. Also, last but not least, the domain size had to be big so that the walls don't interfere with the flat plate, and therefore the resolution on the flat plate may not have been sufficient to capture all the phenomena needed. If we look at convergence, same picture arises. What I do is subtract the analytical solution from the numerical solution and compute average error. We do not reach the desired spatial convergence of 2 that is applicable to Lattice Boltzmann method, but again, this could be due to not fine enough grid, due to the fact that I'm simulating the whole 2D domain, but also probably due to the fact that there is multiple coupling between velocity. There is two-way coupling between velocity and temperature field, and this may bring in a lot of inconsistency. In conclusion, I determined that it is indeed suitable to use Lattice Boltzmann method to model heat velocity coupling. I was able to apply it to different Reynolds number and study the behavior, and I realized it's very efficient and very fast. However, it was very difficult to implement boundary conditions because the solution would be unstable unless it's done correctly. I also noticed that the solution becomes unstable at a higher Reynolds number, which is natural due to the fact that a finer grid is required. And I realized I cannot use high velocities because I'll break the incompressibility assumption. Here on the right, I pasted the ME7751 logo for fun, and thank you for your attention.